switching gears now, we're going to talk about MRI data and what we can learn from the MRI data, particularly on the fusiform face area. And just to remind you, I mentioned last time that the fusiform face area is a region approximately right there on the bottom surface of the brain that responds more in functional MRI when you look at faces than other things. Here it is in 4 subjects. Here it's high response to a wide variety of different faces, much lower response to a whole bunch of different kinds of non-faces, and intermediate responses to things that are only kind of sort of partial like faces. Okay, a few things about it. One, it's very selective. It responds at least twice as strongly to faces as to any non-face stimulus. It's present in essentially every normal subject. In other studies that I didn't have time to fit in here, you can show that it has both inversion effects and composite effects, fitting the behavioral data and the developmental data. And its very existence raises a huge number of questions. And what I wanted to do was take a little bit of time to discuss what I see as the strongest challenge to this simple-minded story I'm serving up right here. Okay? Strongest challenge comes about like this. So I showed you this time course before, the response of the fusiform face area to faces and objects here. Well, the first point to realize is, well, there's some response to things that aren't faces. You can see that there, higher response to objects than staring at a dot. The second idea, this is from Jim Haxby, shown here from an important paper of his in 2001, is he argued that the pattern of response across those pixels or voxels that make up the fusiform face area contains information about other things than faces. Okay? So I'm not going to go through the details, but just to give you an image of this, when you scan with functional MRI, you have these 3-dimensional pixels, and the cortex is basically a sheet, so we can visualize the pattern of response across the different voxels in the FFA as some kind of landscape like this. So suppose you scan people looking at chairs and you see a landscape of response like that across the fusiform face area. Now suppose you scan people looking at cars and you see a different landscape. Haxby's point and his data showed that in fact, if you scan people a bunch looking at different categories of stimuli, you in fact get different patterns of response in the fusiform face area to 2 different categories of things, neither of which is faces. Okay, so these patterns are stably different. You can use that for a whole wonderful method of functional MRI data analysis called multiple voxel pattern analysis that sadly I can't go into now. But Haxby's point was just, look, there's information in the fusiform face area about other stuff beyond faces. Okay, so it's not specialized for faces after all. Okay? Okay. So if you believe in extreme specificity of parts of the brain, as I am wont to, then this is an important challenge. Everybody get this? Okay. So is it true? Well, first of all, he argued in that 2001 paper that it was. And so he said in that paper that regions such as the FFA are not dedicated to representing only human faces, but rather are part of a more extended representation for all objects. Okay, so that's his claim. So then I thought, better check this. I didn't think he'd done everything right, so I did my version of it. We did another experiment, and my postdoc and I found that actually you couldn't discriminate chairs from cars in the fusiform face area. So we published a paper saying, nope, no you can't. Okay. And then, very delightfully, Jim Haxby went back and collaborated with some other people and did another analysis of his same original data and said, whoops, actually, quote, preferred regions for faces and houses are not well suited to object classifications that do not involve faces and houses, respectively. So, not that it's a petty little fight, but actually I was kind of delighted. But I didn't get to gloat for very long because pretty soon one of my very own postdocs found that, oops, actually you scan at high resolution, you can discriminate them. So basically the answer to this is yes, there is information in the fusiform face area that has about other things besides faces. You can look in there and, very weakly, it's not very strong, but if you have enough data and you scan with high enough resolution, you can see that there's information about other stuff in there. Okay, so he was right in the first place. But now, if we step back, we can say, well, what does that mean? Really what we want to know is not just is there information sitting there, but is it used behaviorally? Does it matter, right? It could just be that if, for example, cars look a little bit more like faces than chairs do, then maybe you can discriminate cars from chairs in the face area just because that's what any face system would do. They will deliver different representations for those two things. Maybe you don't actually look there, use that information when you're discriminating cars or chairs. Everybody get the idea? So what we want to know is, do you actually use that information in perception? Is it causally involved? Okay, so we need a causal test. As I think I mentioned last time, functional MRI is wonderful in many ways, but it is not wonderful for telling us what information is actually used in perception. Okay? So we need to go to other methods to do that. And one of the classic methods that's been around for a long time is to test neurological patients, patients with brain damage. Here's a patient whose brain is shown in slices like this here. So these are consecutive slices, and this region right there is a region where he's got brain damage. Okay? And just for comparison, here's my fusiform face area. So these are comparable slices in my brain, and these are activations showing where my face area is. And you can see they're pretty similar. So we don't know that that guy lost his fusiform face area from that lesion in his brain, but it's a decent guess. So what happened to him? What can he see and what can he not see? Well, first of all, he can't recognize faces, like at all. Okay? So that tells us that that region is causally involved in face perception. That's not too surprising. It's nice to know. But really the question we're after is it also involved in perceiving other things beyond faces? And so these guys tested this gentleman, that Wada and Yamamoto tested this gentleman on 4 different tests of object recognition. And he was absolutely normal at all of them. So here's a case where the patient data argues that a region that's causally involved, that's necessary for face recognition, is not necessary at all for object recognition. Consistent with the idea that that region is only involved, even if it has some information in its pattern, some crappy little weak information that might enable you to slightly tell between, say, cars and chairs, it's not causally involved.